Hey guys, in this video, we're going to be tackling this problem you see on the slide. What is the value of the resistor R1 if you want X amount of current running between points A and B? All right, so let's look at the circuit that they give us. It might seem confusing at first, especially because we have two batteries within the same circuit, and it just kind of looks like a mess of everything. We have four different resistors. Let's say that for this problem, they give us the values of E1 and E2, so the EMF of both of those batteries. They also give us the resistor values of R2, R3, and RP. We want to find R1, which is this one in the corner. And they also supply some X amount of current running between points A and B, which let's just label as I1 for future use. So we want to find R1, and we also want to tackle what does the current look like running through the circuit. Okay, so the first thing you want to do when looking at this circuit is choose a place to start. Now, normally that case is easy because we only have one battery, therefore we just started the battery and start drawing out our conventional current arrows. In this case, we have two batteries. The main takeaway here is that for all purposes of drawing the current through this circuit, just choose one battery. It doesn't matter which one you choose. Some people might tell you, okay, choose the battery that has a higher voltage because that will probably be the one that's responsible for pushing all the current through the circuit. But for the purposes of just sketching out how current flows, it doesn't matter. We'll talk later in this video about how to handle voltage drops within the circuit, considering that there are two batteries, but for now, just choose one. Let's start sketching out current leading from the first battery, E1, just because it's the first one, again, arbitrary choice as for now. Remember that we're talking about conventional current, so we're beginning at the positive end of our battery here. Let's call this total current that we're leaving with I1. And remember, that's the same I1 that we said will be running between A and B, so through resistor P here. That same I1 will travel down here, where I've indicated by a pink dot that this is where we now have a junction. So we now have a splitting of current. It could either go left or it could either go down. So whenever you see a junction, you kind of want to remember, okay, we have Kirchhoffs junction law that might come into handy when we deal with the math behind this circuit. So the sum of the current going in, so in this case, I1, should equal the sum of the current going out, which means that we eventually, when we close our junction, the same current I1 should come out. All right. So I1 is coming down. When it splits, let's call this I2. Let's call this I3. I2 will flow through this second battery. Again, just treat it as another circuit element as for now. Just treat it like it's another resistor. It'll go down through R2. Similarly, I3 will just go down through R3 and a left here. Here's where the junction closes. So now I2 plus I3, we are back with I1. I1 will now run through R1, and here we go. We're back at the negative end of our original battery. So that's how you sketch how current flows throughout this battery, and that's very important because it needs to be your first step so that you can then start thinking about how to calculate resistor values. Now, whenever you see complicated circuits like this, I already mentioned Kirchhoffs junction law. You also want to keep in mind Kirchhoffs loop law. These two laws are basically shortcuts. They're hacks that you can use whenever a circuit is complicated, has too many pathways, has too many elements in it, and you need some sort of way to make sense of both potential difference drops as well as current flowing throughout the circuit. So let's identify loops in the circuit that we could potentially use to find our unknown R1 value. One easy loop to see is this outer square loop. Similarly, next we can tackle this inner square. Again, a loop is just any path you can draw throughout a circuit that'll take you from the positive end of the battery all the way to the negative end. So you could have considered more complicated loops, such as going like this throughout the circuit. However, in the interest of this problem, it seems easiest to tackle the loops you can most easily visualize here. If you want to practice with the other loops, feel free to. You should get the same answer and you should be able to calculate the eventual R1 value. But keep in mind that it might take more math as you are introducing more variables and more circuit elements depending on what loops you choose. So with that being said, let's further analyze this outer loop. According to Kirchhoffs Loop Law, the sum of all your voltages in a loop must equal 0. So if we start from the beginning of this loop, starting with the battery, we have a positive voltage associated with the battery, right? The battery contributes voltage to this loop. And any resistors that we encounter will then lead to voltage drops. So we don't know the exact voltage going across RP, but we can calculate it through Ohm's law, V equals IR. So the voltage drop across RP is simply I1 times RP. Similarly, as we continue through the loop, we can have the same relationship for R3. So the voltage across R3 is equal to I3 times R3. And then finally, the last resistor we encounter is R1. So we multiply that by the current going through it, which is I1, for our final voltage drop in this loop. Now, looking at all these values and comparing it to the values we were given to solve this problem, I put check marks under all the variables that we were given and question marks against our things that are still unknown. So our unknowns at this point are I3 as well as R1. Again, R1 is what we ultimately are interested in solving for. So now let's look at this smaller loop right here with the second battery. Okay, so this inner loop, again, we already sketched out how current flows in this inner loop. Let's now think about the voltages. So just to have a starting point, let's start here at the battery. The battery here, when we do Kirchhoff's loop law, we will have it as a positive number, so as a positive voltage. Now, why is that? Because if you look at the direction of the current that we already established, remember this current is based on how it's flowing from this first battery, right? If you look at the setup of E2, this is the negative end, this is the positive end. So had we started from battery number 2, the current going through it would still be to the left. You see that? Because conventional current, it would start at this positive end, it would still move this way. So that's why we can say that this voltage contributed by battery 2 is going along, it's contributing to this circuit. All right? If the orientation of this battery was switched, so let's say the negative end was here, the positive end was here, then when doing the loop law, we would have to put a negative E2, okay? Because then the current supplied by this battery would be going in the opposite way as the current that we already dictated going by battery 1. So in that case, we would have a negative E2. Looking at our scenario here, again, both currents are flowing in the same direction. That means there's a positive E2, and we do the same thing we did with the outer loop. We consider, okay, current is flowing through R2. Let's consider the voltage drop there by multiplying the current times the resistor, and we do the same thing for R3. So if we look at this equation up here, again, the check marks are the things that we are given values for. The question marks, okay, we don't know I2 or I3. However, remember, there's not just the loop law, there's also the junction law that we initially considered when sketching out our current. So junction law says that the sum of the current going into the junction, it has to be the same as the sum of the current going out. That means that I1, so this I1 coming in here, is equal to I2 plus I3. Rearranging that, that means that I2 is equal to I1 minus I3, right? Which means that we can substitute it back into this equation, and we'll only have one variable, which in this case is I3. Now you might be wondering, okay, why did I choose to substitute out I2 instead of I3? Well, the reason for that is because on the previous slide, our unknowns that we got from the equation with the outer loop was R1 and I3. So I have an I3 here. I don't want to eliminate that variable because I want to directly solve for it in this new equation here so that I can get a value for I3 and then plug it back in to this equation and ultimately solve for R1, which again is my whole goal for this problem. So that's just written out in words here. You can solve for I3 now. It's just algebra at this point. You're done with all the physics, with all the circuit logic, and plug that value into equation 1. That was the one I just showed you on the previous slide, and eventually solve for R1. Sorry, this should be a R1 here, not RP. Now, one last thing I like to bring to your attention for this problem is that you could have also started current from the second battery. This is what, in case you're interested, what the current would look like, and I've indicated by subscripts to indicate where, for instance, a junction opens, your current splits, so you should start to label your current values differently too. But it's the same sort of process if you then want to use a loop law and solve for individual current values, and eventually get to solving for R1. So same exact logic, you could have done it either way. Just keep in mind when you use the loop law, consider how the current is flowing across your battery to determine if your EMF in that case will be a positive or negative value. And that's it, guys. If you like this video, please leave a like and subscribe to this channel. As always, leave a comment if there's another STEM topic you're struggling with and would like a video. Bye, guys.